Welcome, everybody. Thanks for joining us again here at Gensyn. We introduced you a short while ago to REE, Gensyn's Reproducible Execution Environment, and spoke to a couple of the engineers that were working on it, behind it, one of whom's joined us again today, James, and today we've got Brian as well. Welcome, gentlemen.
Thank you so much.
Yeah, thank you for having us.
Brian, I don't think you've been up with us before. Do you want to give a bit of an introduction of your role and add a little bit about your history?
Yeah, so I work as a GPU kernel and compiler engineer at Gensyn. I've been with the company for over 3 years now. So I've come to see this entire reproducibility stack kind of from the beginning, conception days, all the way basically to production.
Fantastic. And James, we know you from last time. Welcome back.
That's right. Yeah, thanks. Glad to be back.
And where are you at the moment? Not the tropical background I'm seeing there.
It's pretty close. So I'm in Cannes, France. I'm down here for ECC.
Fantastic. Thank you guys for joining me. We're going to go a little bit more into the technical details of REE today, as we had an excellent introduction last time around. James, before we start though, I think you being in Cannes is probably a good time to mention what you've got going on later today.
Absolutely, yeah. So later today, we have a REE workshop. It'll be at 4:30. We will be doing a hands-on, demo essentially, where you can, everyone who's there can have a chance to download REE, to work through it with me there, as well as with Jesse, who was on our last Twitter space introducing REE with me. We'll be there demoing all of it, going into some of the nitty-gritty details, being able to do a little bit of face-to-face. There is a sign-up link. We would encourage anyone who's down here for EthCC to join. It's just luma.com/EthCC-REE. Again, we'd love to have as many people out there as we can. Love to meet some of you face-to-face. Yeah.
Excellent. So if you are keen on figuring REE out and you happen to be in Cannes, this is probably your last chance to register and join. Going to be an awesome session for everyone who's managed to make it down there, I think. Why don't we kick it straight off? As I know you guys are limited for time today, tell us a little bit about what REE is built out of. What are the components to have a reproducible run in terms of SDK, compiler, kernels, anything you want to add in there?
Yeah, absolutely. So I'll start up this. So as you mentioned, there are sort of a few components in this. Starting from kind of at the top level, we've got an SDK that's going to kind of orchestrate the entire run. It's going to take in some models and it's going to run it through all of our components and kind of stitch everything together to ensure that where we can sort of inject that reproducibility, or rather where we can, all the places where we need to control for reproducibility, it's the SDK that really, serves as kind of the supervisor there. So the SDK will call into our compiler, the Gensyn compiler, which will do some deterministic optimizations and graph rewriting and various things like this. And the compiler will also step through the machine learning graph and find all of the places where there are kernels that would be called that are either not reproducible or just non-deterministic entirely. And the compiler will then replace those kernel indications with indications to our kernels. And so obviously then this leads to, we also have to have kernels, and these kernels must be not only deterministic, but also reproducible, bitwise reproducible across all devices. So these are the actual implementations of the individual operations, whether that's softmax or a matrix multiplication or whatever it is. These have to be completely reproducible across all these different environments. And as Brian mentioned, this is one of the things that he has worked on from the beginning, is building out that kernel library. And so that all kind of comprises together to give us a reproducible run. You have to have all of these things from that top level. This is something that takes in the model and then moves all the way down through compiling it and then actually running the kernels at the end of the day.
So developers and engineers who are trying to use REE or integrate it in some way, what would this be most familiar to them, as if you have an example?
I would probably compare this to using like PyTorch, but a modified model under the hood, right? So ideally, the user experience for anybody that wants to kind of really dive into it is they start with a model. Maybe it's like a Hugging Face model. They kind of do the SDK steps to get the model in the right format and the right positioning, and then they can use it kind of as they would for any Torch model where they want to do generative inference, right? So that's the intention of the workflow. There's other things we've done to kind of make sure it's compatible with just, non-reproducible models as well. We make sure basically we're aligned kind of in all verticals across all three major components, like the SDK, the compiler, and the kernel library. So there's tons to play with, but overall, it's just like working with another Torch model. So
fantastic. So it should be quite familiar to people and intuitive, both within the Gensyn stack and other things they've worked with before. Marvelous.
Yeah, absolutely.
There's obviously going to be many different types of people, organizations working on various implementations of REE. All those different types of hardware setups, all other specifics. How do we handle that variability?
Absolutely. So as you mentioned, everyone's setup is going to be slightly different, and we sort of alluded to this in the last time we chatted about, well, it works on my machine, but wait a minute, it doesn't work on all these other machines, right? So how do we ensure that kind of REE works the way that we expect across all of these devices? So there are essentially, I guess, two main things to note here. One is that we have this sort of machine agnostic view, and this is what the compiler takes. The compiler takes this approach of saying, I'm going to do exactly the same optimizations and exactly the same transformations and do all these translations and whatnot, regardless of the hardware. It's really not going to care about what hardware is under the hood. And this is, I don't want to say unusual for a compiler, but often that's not what you would necessarily expect at the lowest level. When you're dealing with sort of like a low-level compiler, you'd expect it to want to go and look at all the various hardware features and try to eke out all the performance. But that's really not the point of our compiler at this stage, right? At this phase that I'm talking about. Because this point is just, let's make the model reproducible. Let's make the model compute graph, or the compute graph that represents the model. Let's make sure that that is set up in such a way that we can always do the exact same thing across any of these pieces of hardware. Mm-hmm. Then we get down into actually invoking the kernels themselves. And there are a bunch of different tricks that sort of can be played here. I think Brian would probably be a better person to kind of detail some of the high level things that we do there, being a kernel engineer. So I'll hand it over to Brian.
Yeah, so I mean, if you think about some of the major sources of differences on different hardware levels, some of it's as simple as like, how do you like calculate like a certain math function, right? Like how do you sum up like three numbers? That's like the base example of non-reproducible compute, right? So, hardware A might say it's A plus B plus C. Hardware B might say it's A plus C plus B. And as we kind of all know in floating point math, that actually could lead to a different output. So that's one base example. There's other ones too, more complex ones like random number generators, right? Well, how do you make a bunch of random number generators behave the same? There's ways to do it, but if you just take the de facto random number generator from NVIDIA or CPU or whatever it is, you'll get very different behavior across the spectrum of devices. So there's things like that we have to think a lot about. And a lot of the implementation and tricks are addressing those hardships explicitly for users, so they don't have to think about it.
Excellent. Absolutely. And correct me if I'm wrong here. Sorry, Xavier. Correct me if I'm wrong here, Brian. I think one of the other things too to note is that we sort of get I don't know if luxury is the right word, but for sure part of what you do is looking for ways to try to avoid sort of this combinatorial explosion of, okay, now I want to bring out these new types of hardware. How can we sort of make sure that we're architecting things from the outset where we're not going to have to go and completely rewrite our entire kernel library, right? There's a lot of sort of I don't want to necessarily call it secret sauce, but quite a lot of thought that goes into architecting those kernels from the get-go. So it's not just, okay, it works on this one type of GPU and this one type of CPU together, but really we know that, okay, as we bring up all these different, whether it's NVIDIA GPU types or whatever, that they can all sort of adhere to the same specification that we've constructed.
Yeah, that's completely correct. I think the way we've designed and architected the kernel library is that any hardware, assuming you just have an implementation that works for it, should quote unquote just work. And I say that with caveats because not every hardware, like if you dive deep into it, like you'll find that not every hardware supports things out of the box as you would hope so. So then there's a bit of like dancing you have to do to make it kind of work for you. So I would encourage people to play with REE and maybe experiment with the ideas and see what kind of challenges they run into. I think that would be interesting.
We'd like people to try and break it.
Yeah, I would say that if they can break it, that's great because we figure out where things don't work, we fix it, and we make REE more robust overall. So.
Absolutely, that's what we're here for.
That process, or that dancing, as you referred to it. How creative did you have to be to bring all of these different pieces that people are going to be attempting to use in together?
Well, I would say it depends on like what level of complexity you're going for. If you're trying to just solve it, it's less dancing. But if you're trying to solve it and make it performant, then you start doing a lot of dancing. And then if you start to go down this line of performance and like, okay, like can we support like every flavor of a data type or every flavor of like a math function or whatever it might be, then the dance goes kind of from like a slow dance to like a full on like Macarena or a full on tango, right? Like you're basically just juggling a bunch of things. And we've already dealt with this a few ways. I won't go into all the details, but in theory, all of these problems can be solved. It's just the solutions to them are not always super clear. So
I can't wait to see you at the work Christmas party. In terms of solving for different use cases, different setups, different hardware, and that kind of thing, are there any restrictions on REE currently? What about model sizes and things along those lines?
Absolutely, yes. So the current release of REE is intended to be, I don't want to call it a beta, but it is intended to be a very early release. Mm-hmm. So we have intentionally scoped it to very specific restrictions. So the maximum model size that we currently support is about the 32B model, or 32 billion parameter size. And people are welcome to try it out with larger than that and see how far they can push it. But that is, as far as we're officially supporting, that's kind of the goal. We also intend to, or rather with the current release, it is intended that it only works on a single GPU device. There's no parallelism. We also only support NVIDIA GPUs within a specific kind of generational range. That all that is listed on our website. But that is intended specifically for this release. But just so that people know, that is intended for this specific release. So if you have specific requirements, or hey, I really want to make it work on this specific device or this specific model, please just drop us a line. Know that we know that this is not the end all be all. This was never intended to be, okay, this is the thing that, this particular release solves it for every hardware, for every model. Because there's still lots more ground to cover, and we're very happy to be covering it.
The difference in models that you were talking about then, models are changing, new models being released. Models seem to be doing things that people didn't think possible. If we were reading recent reports on hardware they didn't think possible. How are you keeping up with that?
A lot of I was gonna say a lot of coffee, but as I'm the guy, one of the few people at the company that doesn't actually drink coffee. But no, I mean, I think, I would say that it does come down to this is something that we just really love to do, and so staying up to date on those things is something that we all find very interesting and exciting and fun. We love to see these types of huge milestones and leaps forward. And anytime we hear about one of these, it's, oh, okay, cool. How do we make this reproducible? And how can we kind of take it the next step so that it's, we can make it so that whatever this researcher has developed, how can we make that actually out in the world in a reproducible fashion? Yeah, so it's. I don't actually want to say it's a lot of late nights or anything like that. It really is just we all really love what we do, and we constantly keep our ear to the ground.
Yeah, I would say that goes both for models and for hardware, right? Like, there's some hardware that we've been looking at that I won't go too much into detail on that, but like everything has a new feature, more or less. Like it's whether it's a new model, a new hardware. So we always think about how we can incorporate that in our stack. And so far, it's been a very smooth process with the way we've designed everything. So
this feeling of discovery just permeates through everything that we've been speaking about over the last couple of months. Absolutely love it. Brian, earlier on you mentioned that it was basically a custom version of PyTorch that people would be using. Why wouldn't we use the regular version or any other system that's already out there?
Yeah, so the regular version of PyTorch will have all the non-reproducible ops. But then if you kind of go down the rabbit hole, like there's other concerns with just like kind of vanilla torch, like infinite kind of loops or like malicious code that people can inject in PyTorch modules. So we have kind of a process where we make sure that the graph is safe and that we know that we can trust whatever goes into kind of the system. So we have a vetting process. I won't go too much into details because it gets very complex very quickly. But we have a way of ensuring that the model and the graph are safe, that it works, that it runs, that it's doing what it should do. And then we inject that essentially into our compiler stack. The other reason for this is at some point, like we will start to be a lot more performance oriented. And we've already kind of paved a path for this going forward. It's literally just a matter of time where the compiler will allow us to just start doing things like fusing ops or making like super kernels and things like that are reproducible, but they're like super performant for whatever hardware targets we care about. So I would say like that's the main reason to not just use Torch. And there's others too, but I would say that.
So there was reproducibility that you were effectively adding, but also it sounds like there was various elements of hardening that you were doing as well. Why did that need to be done? They're fairly important topics to many industries. Why were they still left open?
Great question. So our initial vision for Gensyn, right, and I think it still holds, is that it's a decentralized kind of platform, right? So the idea is that if someone provides a model that they want trained and someone else is going to take that model, or even just inference, like it doesn't have this to be training, someone else is going to take that model and run it, you have to know that there's some level of security with that model, right? Mm-hmm. You don't want, and actually probably worth mentioning, if you've looked at what's happened the last few weeks, there's been a bunch of hacks on like very popular open source like software packages where people's information's getting leaked, ransomware. It's like, it's crazy. This is happening at such a higher cadence than ever, especially because of like the agentic AI world that we live in now, right? So the idea that we need like a validation layer, a verification layer to know that the model that somebody else is providing is safe is like essential. And then on top of that, you need to actually, what we believe as a kind of a philosophical point of REE is we need to be able to verify what you actually compute is accurate, and that if you wanted to go take that same computation and run it on a different set of hardware, you'd be able to get the exact same result, the exact same computation order. So those, I say, were the main reasons why we have these extra layers in the stack.
So why PyTorch at all? Why would we build our own custom runtime to solve for all of those issues?
I'll probably share this answer both, James, but my general belief is we wanted to pick a framework that people actually are comfortable using, that works easily. Torch has some nice support for custom kernel implementations that we definitely like to take advantage of. But it's also just like, if you look at the ecosystem of ML, it's by far won the market share for like the most common ML framework from both a training point of view. Mm-hmm. And I think it's starting to win more market share in terms of inference. So it's kind of just naturally compatible with like what people use, what developers use. So that's kind of the base idea. We could do a custom runtime, but then there's this ongoing tension that's always been there between how do you make like awesome hardware easy to use from a software point of view, and if you reinvent the wheel, that becomes a big challenge. So
yeah, absolutely. It makes me think of that XKCD of, oh, you look at all the competing standards, and I'm gonna build one that solves all of these, and it's like, okay, well now you just invented a new standard, right? Mm-hmm. And so I think for us, there were a few things that really went into the decision, and one of them was we looked at the machine learning engineers here at the company and said, what do you like to use? What would you pick? Right? If someone came to you with a new library and said, hey, please try this, what if it's in this framework or that framework, what framework would you want it to be attached to? And people said PyTorch. Okay, well, let's go pick PyTorch.
Fantastic. All the work, as you said, why reinvent the wheel when half the work is already done? Something people are comfortable using. What was the hardest thing you had to solve, either of you or both of you, throughout this entire development?
Yeah, the hardest thing to solve throughout this entire development, I would say, is there's definitely coming from sort of I won't say traditional compiler approach, because how long have we had ML compilers? Like really, it's not that long in the grand scheme of things. But there's definitely a big focus on performance. And this idea of shifting my mindset of I need to focus primarily on determinism and reproducibility, primarily on ensuring that all of these, like that the graph is safe, that all of our optimizations are not only correctness preserving, but reproducibility preserving, is just a very different problem than I would say most people really focus on as a compiler engineer. And one of the kind of lower level problems that showcases that is there's what we call provenance, compiler provenance. And it's this idea that I want to be able to work backwards. So after the compiler runs, it spits out its compiler artifact. I want to, at any given time, be able to work backwards to the original input to the compiler from those artifacts. This is very atypical of a compiler. It is not often that you can work your way back from and get the inputs given the outputs of a compiler. But this is something that we really need to be able to prove that it's working the way that we want to. And also just personally, selfishly, something that I really needed to be able to debug anytime I did something wrong. And so that was just a very difficult sort of approach to make sure that throughout all of the compilation, we were able to keep track of that provenance all the way down.
So you effectively had to reverse the flow entirely from what you're used to working in.
Exactly.
Reverse the polarity. Brian, what was your most difficult solve?
I would say it's probably a continuum for me of what you would assume to be reproducible is not always necessarily reproducible, which I think is is interesting. Like, to give like a concrete example, if you try to broadcast like two tensors of different lengths, like in an addition or a multiply, on the forward pass, like, oh, that's naive math. Like, there's a fixed way to do this. Like, there's no complexity. It's two operands. But on the backwards pass of that implementation, what you find is that there's some sort of summation logic for actually computing the gradient. And the way that every hardware computes that summation might not actually be the same ordering. Mm-hmm. So there's things like that where it's like, you think you really know what you're doing. You think you've really solved a problem. You've like assumed things. And then you realize very quickly, okay, that's not necessarily the case. Now I need to kind of think about why that's not the case and then figure out what the solution for that is. And there's a bunch of instances of that I feel like you run into. Even in like pre-processing or like post-processing code, right? Like you're doing some generative inference for an LLM, you need to do a sampling layer. Well, turns out not every sampling implementation is reproducible. Some are going to yield different results on different hardware. So there's things like that where we have to be very intentional about what we use and what we implement. So I would say those are probably the hardest challenges we deal with.
Excellent. Thank you very much, both Brian and James, for joining me today. A fascinating look, a little bit deeper under the hood of REE. Anybody who does want to find out more and is in Cannes, you've got a very short time to register and attend the workshop. And don't forget, there's also the AIRL Cannes, hosted by Gensyn, the casual mixer down by the beach this evening as well. I'll pop links up for both of those. One last question for you both. Where is REE going from here?
To the moon, of course. I mean, I would say, I sort of alluded to this earlier, but one of our main focuses is how do we stay up to date with the latest and greatest, the largest, the smallest, the newest hardware, even how do we reach out sort of back to existing hardware that is just kind of hanging out that maybe we haven't supported yet. So really broadening that scope is something that's kind of top of mind for me, and making sure that we can increase that compatibility and meet people where they're at, no matter what device they're using, no matter what model they're using, and really making sure that we are as spread as broadly as possible.
Awesome. Love to see it, Brian.
Yeah, I would add to that, right? It's like we could do so much right now. Like we could jump in like 4, 5, 6 different directions. Mm-hmm. But I think what we really appreciate is like having community feedback to figure out like what direction immediately it helps end users as best as possible. So there's a lot coming. Let's just say that.
Excellent. Can't wait to see it. Can't wait to have you both back to talk through it as well. Thank you both again. Enjoy the rest of your days. I know most of us probably like to be on that beach there with James. Everybody out there, make sure you get into the insides of REE and start playing with it, experimenting, try and break it, build it into whatever you imagine. And if you have any trouble or just want to ask some questions or discuss what you've built, make sure to get in touch, pop into the Discord or on Twitter. And lots and lots of people very, very happy to take up those conversations with you. Thank you, gentlemen. Speak to you again soon.
Absolutely. Thanks so much.
Thanks, Xavier.